Hi everyone, Dr. Madi here, and this is another lesson in my robotics lessons series. In this video, I will show you how to work with the Python ROS API, control the robot in joint space, and then do a simple pick and place task with the robot. As always, remember that for simulation, you do not need the physical robot. Here you see some implementations from my amazing students for this activity. Just a reminder that the lessons are gathered in a playlist, and there is a GitHub wiki that complements these lessons, and you can easily copy the code from there. The initial lessons in there are prerequisites for this activity, so make sure to do them first. Now that we have successfully installed the ROS interface and have interacted with the robot in simulation and reality, it is time to work with the Python ROS interface. Note that this requires that you have already installed the ROS interface, which sits on top of the ROS interface, and you can easily control the robot using a bunch of Python code, even if you do not know how to work with ROS. Important note, there will be a lot of terminology associated with this interface, like base frame, space frame, transformation, pose, etc. in the code. If you encounter these, do not fret, because in this activity, we want to see the end of the movie first, and we will go back and study all of these terminologies again. For now, do not worry about them and follow the activity to get a peek at how the robot works. Here you are seeing some implementations by students in the previous semesters. Now let's see the functionality of the Python API with a couple of examples. The objective of this activity is to control the position of individual joints on the robot arm. First, open up a terminal by pressing Ctrl+Alt+T. Then, run the command shown here to launch the robot arm in simulation. Note that the reason we do it first in simulation is that if we impose a certain pose on the real robot that is beyond its limit, we can damage our robot arm. So make sure that everything works fine in the simulation before trying it on the robot. In this command, we launched the launch file named xs-armcontrol launch from the Robotics xs arm control package. It configures the launch to use the px100 robot model and enables simulation mode, use sim equals true. Note that a launch file in ROS2 is used to start and configure various nodes. By running this code, you will have the robot in the RViz environment. Now, using the following code, you can control the joint positions. They are in radians. The joint positions in this code are intentionally missing. First, go to the class activity1 and look at the table containing the joint limits. After that, fill in the blanks with proper joint angles in radians. Make a .py file in the Visual Studio Code and put your code there, and then save it as joint control px100.py in the current directory. This Python code uses the Robotics manipulator XS class from the Robotics XS modules.xsrobot.arm module to control our robot arm. Locate Robotics manipulator XS class within arm.py and see what functionalities it can give to our robot arm. Now, to test your understanding from our Python course, answer this question. In the code snippet, the Robotics manipulator XS class from the Robotics XS modules.xsrobot.arm module is employed to control our robotic arm. Could you elaborate on how this code demonstrates the principles of classes and objects in Python? In particular, how does the code create an instance of the Robotics manipulator XS class to represent the robotic arm? How are the object methods such as go to home pose, set joint positions, and go to sleep pose utilized to interact with the robotic arm? Now run your code right from the VS Code. You should observe that first, the robot goes to the home position in simulation. Each joint moves to the specified positions, then goes to the home pose, and finally to the sleep pose. If everything works fine in the simulation and the joint positions are attainable by the robot arm, go to next step to run the physical robot. Now you can repeat the instructions, but this time without the use sim argument, to see your implementation on the robot arm. Note that this is just a simple pick and place and does not use any sensor such as a camera for feedback. First, follow the same method as the previous example to open the simulator to test, and then on the physical robot arm. Write a code similar to the code shown here and save it as pickandplace.py in the current directory, later to perform a simple pick and place task. Try to pick up one of the cubes, rotate and toss it somewhere like into a bin, etc. Use your imagination, but be sure what you ask the robot to do is within its capabilities. The safe and recommended control sequence for the robot arm through a series of movements from its sleep pose is as follows. Command the arm to go to its home pose. Command the waist joint until the end effector is pointing in the desired direction. If you want it to be in the home pose, then do not rotate the waist. Command poses to the end effector using the set EE Cartesian trajectory, grasp, and release functions as many times as necessary to do a task, pick, place, etc. These functions are defined in ARMPy library. Repeat these steps as necessary. Command the arm to its home pose. Command the arm to its sleep pose. You should complete this code with your imagined scenario. Important, do not replicate the code because it is just an example and not necessarily doable by our robot arm. Here you can see some of the implementations by my students. According to the Python programming lesson, an arm.py library explain how this code works in terms of classes and objects. Using the arm.py library, explain what set single joint position and set EE Cartesian trajectory do. Don't overthink and do not get bogged down with the terminology that we will study later, like orientation, rotation matrices, transformation, etc. Just in simple words, what is your understanding of these functions? Set EE Cartesian trajectory function makes the linear displacement along the x, y, and z axis possible. How are these x, y, and z are calculated based on the arm.py library? Do not worry about the terminology here. You do not want to be exact. For example, you can say it is the distance in meters from the base frame, etc. Just report on your observation from experimenting on the robot arm. Using the gripper.py library, explain what the grasp, release, and set pressure functions do. Let me know if you have completed this activity and the code works, or if you have any questions. That's going to do it for this activity. I hope you write the code and at least implement it in a simulation. Note that you do not need the physical robot to run the simulations.